All right, so now that we have an idea of how to write and interpret chemical formulas for different substances, ionic and covalent, we're going to put all that into practice now and incorporate them into probably one of the more fundamental and important concepts in chemistry, which is the idea of chemical reactions and then chemical equations, which are used to represent those reactions. So when we talk about chemical reactions, those are nothing more than chemical changes, and we can represent them by using chemical equations. So what we're going to do is take a look at how we write, how we interpret a chemical equation, how we can classify them, and then also, more importantly, how we actually use them to solve problems. So when we talk about an equation, we can use a simple example to illustrate what we're talking about. So let's say, for example, we have the following. Let's say that hydrogen, we're looking at this chemical change. So hydrogen gas reacts with oxygen gas to produce, we'll say liquid water, right? So that's a normal sentence filled with words that you're used to. We can take that and we can translate it into a chemical equation as follows. So hydrogen gas, so we know hydrogen, based on what we talked about previously, hydrogen exists as a diatomic molecule, so it's H2. And as a gas, what we use to show that, well, this is the physical state of this particular thing, we use G, lowercase g in parentheses. So this means H2G means hydrogen gas, and then reacts with, we use a plus sign to represent that. So that means reacting with, and then oxygen gas, we know oxygen is also a diatomic molecule, so it's O2. And then for gas, we're going to use G to represent the state, physical state of it. And then to produce or to make or produces or makes, we use an arrow, and the arrow always points from left to right. And then we're going to make liquid water in this case. So water, as we know now, is H2O, and it's a liquid. So you can probably guess we're going to use L, lowercase l, to represent that physical state. And this is an example of just a simple but a very useful way to introduce chemical equations. So whether we have a chemical change represented as shown in the first sentence, or whether it's shown by a chemical equation, it should give us all the information that we need. So we haven't lost anything going from this sentence into the equation itself. We still have all the information, but it's way more concise and succinct, and it's a lot quicker to write. We need to know how to interpret these, right? So this is our starting point for looking at our chemical equation. So let's sort of orient ourselves now and identify some of these different parts of this chemical equation. So the arrow is key here. This always points from the left side to the right side. And on the left side of the arrow, whatever we have on the left side, these are known as reactants collectively. And you may have multiple reactants, you can have just one reactant. It just kind of depends um, on the equation that we're looking at for the reaction. On the right side, anything to the right side of the arrow, these are known as products. In this case, we just have one product, but we can have multiple products again. So reactants are on the left, and products are going to be on the right side. Okay, that's a general layout. And then the arrow here means produces or makes the stuff on the right. The other thing that we'll see is uh, the things that we're highlighting here in green. Okay, so these are known as the physical states or the state symbols. And there are several of these that we're going to encounter. We already just looked at two of them. So G means gas. L is liquid. And the third one we talked about is a solid, so that's S, lowercase s. There's a fourth one that we're going to see, which is AQ, and that stands for aqueous. And what aqueous means is that that thing, whatever it is dissolved in water. Okay, those are the four state symbols that we're going to see. In some instances, in some cases, what you may also see is something written either above or below the arrow. And whenever you see that, that tells you that those are some special conditions for that reaction to happen. So anything written above or below the arrow, those are just special conditions. So there's one in particular that you may encounter that we will see. And sometimes heat is needed for a reaction to happen. And we represent that by using a triangle, right? So here, now we've seen a triangle before, right, in a different setting where it meant delta, which meant change in something. When you see it in a chemical reaction, below the arrow, for example, that means heat. Okay, so we can say that that is heat that's required for the reaction to occur. Okay, so those are the common symbols that are used to represent what's in quote that we're going to see in these chemical equations. Reactants on the left side of the arrow, products are on the right side of the arrow. So a couple things now to keep in mind when we are using a chemical equation, and it's a very important rule, very important law to be more specific, and that is the law of conservation of matter. So when using chemical equations, okay, we need to follow the law of conservation. And the way that this applies to the chemical equation, so essentially law of conservation of matter says that you cannot create or destroy things, right? So you can't make something out of nothing and things just don't disappear. What does happen in a chemical equation for a chemical change, right? We rearrange things. So from a practical perspective, what this means is that the number and types of atoms on the reactant side, so the left side, must equal the number and types of atoms on the right side, which is the product side. Okay, and in order to not violate the law of conservation of matter, what we need to do with any chemical equation is we need to ensure that that equation is balanced, right? So we're going to balance our chemical equation. So we'll take a look at the first one that we just introduced. All right, so we have H2. I'm going to omit the state symbols just for simplicity's sake for right now, so we don't clog up our equation. And when you balance equations, what would be a good first step would be to just list the atoms that you have. And you should have the same atoms, the same types of atoms on the left side and on the right side. So obviously here I have H on the left side, on the right I have O on the left and the right. And what I'm going to do is just make an inventory of how many of each I have. So on the left side here, I have 2 hydrogens. On the right side, I have 2 hydrogens. On the left side, I have 2 O's. Now on the right side, my O is here in the H2O. Remember, if you don't see a subscript, 1 is understood to be there. So I have 1 oxygen. Okay, so I have the same number of H's on both sides, which is good. But my oxygens are not the same, right? So I have 2 O's on the left, 1 O on the right. Obviously, according to the law of conservation, that can't happen. So I need to balance the equation. The way that we balance the equation is we're going to use things known as coefficients. And what coefficients are just simply small whole numbers that we use that are placed in front of the formula for that particular substance in the equation. So the way that I like to balance is I write my equation and I put a line in front of each of the reactants and products so I know where my coefficient is going to go. All right. So we already established H's are good, okay, on the left and on the right. My O's are not. I need to make 2 oxygens on the right side. So I cannot change the subscript because then I change what this is. The only thing I can do is put a coefficient in front of. So whatever I put in front here, okay, in this region, gets multiplied by the subscripts of each of the things that I have in the formula. So if I want to make 2 oxygens, and obviously I need a 2 here, so 2 times the 1 is going to give me 2 oxygens. I'm going to change that now. But there's something other than O in water, right? There's also hydrogen. So now 2 times 2 is going to give me 4 H's. So now I make my hydrogens out of balance. Well, how do I make 4 H's on the left side? Well, 2 times something should give me 4. Well, 2 times 2 is 4. Okay, so now my H's are balanced, my O's are balanced, so this is going to be my balanced equation. Now, when you don't see a coefficient in front of something, okay, 1 is understood to be there. Okay, you don't need to put the 1 in, or you can put it in if you want, if it makes you feel better, but it's not 0, in other words, right? So it's 1 or it's just understood to be there. So this is generally the steps that you're going to want to take when you balance an equation. Obviously, this is a fairly simple and straightforward one, but we're going to practice some other ones here in a little bit, and I'll show you some techniques to balance your equations. All right, so again, chemical equations are nothing more than representations of chemical changes or chemical reactions. The general anatomy of an equation, reactants on the left side of the arrow, products on the right side of the arrow. We have our state symbols that are used to tell us the physical states, and then any special symbols other that are used as well. And then before we use any chemical equation, we need to make sure that it is balanced, right? So in the next couple of videos, we'll go through some more examples, but we want to try to get the smallest whole number ratios possible when we balance our chemical equations.